welcome back after our keynote Kay, who I hope you've all enjoyed her talk. We are now switching tracks, and this is the first talk of the transformational ML and AI track, which will be run from 15 to 15, from 14:45 to 17:30, followed by a keynote by Rajiv. Right now, our next speaker will be talking about upgrading noise suppression technology. Noise suppression during audio calls is expected from any real-time communication platform. Good denoising means exhaustive use of modern neural networks. AI also implies heavily processing. Real-time requires speed, and a large number of calls means a large need for resources. Therefore, the questions are, can clients do the necessary work of processing, and can AI solutions be integrated on the client side? Our next speaker will present a neural network for noise suppression implemented as part of the Infobip's WebRTC platform. A generic way of integrating AI solutions with client-side JavaScript will be described, with a special focus on real-time requirements. Please welcome to the stage Sead. It's okay. Thank you for joining us.
Hello, everyone. As a colleague said, my name is Sead Delalic. Currently, I'm working as a senior teaching assistant at the Faculty of Science at University of Sarajevo. But what's more important for this presentation is that I am working as an AI consultant for a software company called Infobip. Just let me see, is it working? Okay, great. So in this presentation, I will talk a little about our company, about myself, just to get a little background. After that, I will describe you a problem that we were trying to solve. What problems did we have there? And after that, we will see the proposed AI solution. We will see how we did an implementation as part of the JavaScript SDK for our platform. And at the end, probably the most interesting part will be our examples and just conclusion. So you can go home. Yeah. Okay. Infobip is a large software company. Probably one of the largest in this part of Europe, with more than 4,000 employees, with offices all around the world, with more than 10 development offices. So as you can see, it's a large communication platform. They are trying to make a platform where you can reach to anyone in the world. And some of the clients are, for example, Meta or Facebook, Uber, Raiffeisen Bank, etc. And some of those, there are more, but just I'm not sure am I allowed to mention all of that. Who am I? I'm allowed to mention that. I got my PhD in computer science at the University of Sarajevo. Mostly I worked on optimization problems and data mining. After that, I started working as an AI consultant at Infobip, but before that, I have more than 5 years in industry of AI, so working on real-world projects. And of course, at the same time, for the university, I had to do a little research, so I had more than 25 research papers, books, etc. Okay. So I will now start with the problem. I will explain what were we working on. When I started in Infobip at the beginning of this year, one of the first projects we actually had to do is denoising system. So we got really huge specifications. Remove noise from audio calls. We got some ideas. Maybe we could remove everything or something like that. So they added something more to that specification. Don't remove anything useful. And literally, that was everything. We know what denoising is, but we just don't have anything more to specify. So we actually did little research, and then after that, we got a few questions. First of all, which signal do we consider noise? What types of nodes are we interested in? Because there are many things that we can consider as noise in real-time communication. So which types of noises are we actually trying to remove? After that, maybe smarter question is which signal is useful. So can we just find what's useful and remove everything else? And of course, what actually was the biggest problem of all is how fast should it work? I mean, probably should we do everything in real time, or do we have a time for post-processing after the call is done, and so on? So here are our answers. First of all, we are interested in hearing the voice of the person speaking. So basically, those are just regular calls with 2 or more clients. And we are trying to see what types of noise do we need to remove from there. There is something called static noise. There are some noises from different devices around us. For example, air conditioners, some other hardware devices, and so on. There is some chatting babble in the background, so we are actually trying to remove that as well. And there is typing sound, which is basically encountered on everyday basis in call centers. So as I just said, we were actually trying to implement denoising system for Infobip platform, which is basically a platform mostly for call centers. When you are trying to reach to some agent, he's trying to help you, and basically that's the greatest use case of all. And everything should be in real time. So there are some papers which said that you have under 200 milliseconds to do everything. Just when I say something, so we have 200 milliseconds, so you need to hear everything, or you will see a delay, which is actually really irritating. In real world, you have much less than that. So you have around 100 milliseconds to send data, to pre-process everything, to use a neural network and do everything you need to do, so the other client could hear what you were trying to say. As I said, this had to be implemented as part of something called WebRTC platform, which is basically Infobip platform, Infobip's platform for like Teams, Google Meet, etc. There you can have calls one-on-one, so just 2 clients talking with each other. But at the same time, you have something called conferences where, I mean, you have many different clients which are actually trying to exchange data and their opinions. How it's all working in real world. So basically, you have few clients around the world. They are all sending data to Infobip's platform. And then on that platform, you have to see how to reach to other customer and just what type of routing you have to do there. So as you can see, with many calls in a day, with many conferences and everything else, to do the denoising part at the center here, where Infobip platform is, would be really exhaustive. And I mean, it would be hard, and harder resources, a lot of them would be used. So it's just not that practical. So if you have a client with some types of noise, maybe it would be smarter to do the denoising part on his side. So maybe even before the sound is sent to our platform, maybe we should try to do the denoising part there and just send denoised sound to center platform. Of course, as we know, for client side, I mean, you need to implement something in JavaScript, which is not that useful, not that actually something you need to do in everyday's life when you are doing an AI. So how we did everything. First of all, we did our research on denoising. In denoising world, you have 2 types of algorithms. First of all, we have standard approaches, which are actually mathematical filters. So you have some filter, everything you got of the sound, you are trying to see what will happen when you apply that filter. But these algorithms are not working well. And basically, if they are working well, then they are slow. So those approaches are just not that useful in today's world. At the same time, there are, of course, AI approach for everything that we don't know how to solve in standard algorithms. So basically, there are two ways to do this problem, to tackle this problem in AI language. For example, we have recurrent neural networks, and we have something called autoencoders. In our team, we implemented a few of those solutions, and I will present you the one that's working the best of all of them. Okay, so in next few slides, I will try to explain you all necessary steps for AI solution, which is actually implemented as part of our platform. I will give you an example how to create data set, how to pre-process everything, which neural network to use, how did we do our training, and of course, how to use this neural network in JavaScript. Okay, so as part of all neural network solutions, you need to have data. I mean, it's just impossible to record at the same time the same sound with noise and without noise. So you just need to do something smarter than that, and that smarter actually is something called synthesis, where we are having some clean speeches, and at the same time we have some noises, and then we are trying to combine them to one sound, which is actually a speech with noise in the background. We collected few data sets. One of them is called MSSNSD, which is Microsoft dataset for one open challenge. We actually had to buy some other data sets which contains noises and so on. So we collected many open source and some paid data. And we actually did this synthesis where we combined those with different speech-to-noise ratios and so on. And as a network input, what's expected to use noisy speech, and at the same time, you have output because you just started with clean speech, so that should be the output for your neural network, so that part actually went great. After that, the pre-processing part, which is basically, I mean, you need to know what neural network you need to use to see which pre-processing is appropriate. In this presentation, I will describe something called RNNoise, which is recurrent neural network implemented by Jean-Marc Valin. He's really good in this job. So we used his network, we retrained it, and did some small modifications, but at the base, it's his neural network that we are using. I mean, you can find it online, so it's just a neural network. I will show you the model in next slides. Then pre-processing part, which is actually a lot of math. Those are a few steps you need to take. I will not read them. Now I will show you each one of them. So you have complete raw audio. After that, you need to divide this audio into few chunks. We used 40 milliseconds, but we are not denoising 40 milliseconds, we are denoising 20. So basically you have those overlaps over here, as you can see. And why we did that? Why 20 milliseconds? Because it seemed appropriate, and we tested few different versions, but this one worked well in real time. So you are adding a delay of 20 milliseconds to the call, and the pre-processing part is fast, neural network is fast, so you just don't add much delay, so it worked well in our conditions. When we have one of those chunks, what do we do with that? First of all, we need to implement something called fast Fourier transform. I will not explain the math behind it. It's something like this. So basically, this is a job a mathematician called Fourier did, and this is how we did the same thing. I mean, you needed to add another FFT at the end, so it's not that simple. So, I mean, if you know what it's doing, then, I mean, the implementation in today's world are really not that hard. Fast Fourier transform is actually trying to extract different frequencies in the sound. And when we have those, then there are too many values to do in real time. And it's just not necessary to do all of that in real time. What we did, we actually implemented something called MEL filter bank. I mean, humans just cannot hear frequencies in same resolution. And I mean, we just don't hear each frequency the same. So we can group them to get less frequencies at the same time, and then to get a better spectrogram. So this is the complete solution after we implemented something called MFCC. So that image actually is something that we used as an input to our neural network with some additional things like calculating some deltas, but this is just simple math behind all of that. So the neural network is presented here. As you can see, we need only 48 inputs. 24 of them are from that image before, and then 24 of them are calculated with just simple math. After that, this is the neural network. You can see there are some GRU layers, which means that this neural network is actually, I mean, it's a recurrent neural network. And as an output, we got denoised 24 values, which are actually something called gains that we just multiply with original values. As you can see here, what's really important, this neural network has under 1 million parameters, so it's really small. It can be implemented on Raspberry Pis and so on. So basically, it's just meant to be for real-time implementation. Okay, what did we use for training? This is standard procedure, actually. We used MLflow, Python Jupyter, and of course TensorFlow for Keras and TensorFlow for neural network. Training part was actually not that easy and fast, so we used some cloud solutions from Azure, and of course everything was trained on GPU of Tesla, but it's important to say that for inference you just don't need anything. It can be done on really simple devices and simple hardwares. Okay, so now let's get into the part of the WebRTC implementation. So as I already said, WebRTC is basically Teams, Google Meet, Zoom, and so on. So you have clients which are communicating between each other. And in JavaScript world, you have something called Web Audio API, which is basically used for controlling the audio on the web. You can add different types of filters there. You can create some cool visualizations. You can add different effects. You can choose different sources from your machine and so on. So, I mean, basically, this is intended for these types of job. But what's important there is that you can also create something called custom processor nodes. Custom processing is just used for something that we need to have here. And there, of course, is a trick in that because you cannot then add any libraries, anything which is external sources. So basically, you just cannot add neural network to that. So if you are just implementing those custom processors, then you are just I mean, you don't have much options to do. So how it's all working? Maybe next slide will show it better. We have something called audio worklet, which is basically that I described before. You have the audio there, but you are just not able to do any heavy processing there. So we are sending those noisy data, noisy window to main thread. Main thread just cannot be blocked so you need to have click events and so on. There were actually some funny stories for other time during that implementation and blocking everything when customer is moving mouse and so on. So basically what we needed to do here, we just transferred that data to some worker, and there we did all pre-processing, everything actually with neural network and so on, and then we returned those data to audio worklet, and that worked actually fine. Okay. Why we did everything that, this may be interesting for some developers here. We used something called num.js and TensorFlow.js for our implementation, and those are those libraries that we just couldn't integrate to audio web API. I mean, those are similar libraries as NumPy and TensorFlow, but just they have some restrictions, and they are not that fast, but they are actually working really well, and they are getting better over time. Okay, so let's see a few examples which are actually recorded from our WebRTC platform. So this is actually a solution we have currently. This is the original audio. So my colleague was reading something that's Infobip motto, let's say. So you will hear this sentence a few times in this presentation.
We are the humble engineers led by our philosophy of learning by doing and fueled by our passion for technology. We value creativity, persistence, and innovation, integrity, and living meaningful lives are the foundation of all our values.
Okay, so we all heard typing, which is really irritating. He was trying too hard to make you hear typing, but this was our first version of our neural network. Yeah, we were actually really happy about that because we could hear something that's happening, so that's good. Not that good when you show it to someone, but okay. And then this is our improved version. Yeah, you just cannot hear any noise, so it's working well on that part. But at the same time, we removed everything. And after many iterations, this is actually, let's say, a final solution. And then I will give you a few comments about that.
We are the humble engineers led by our philosophy of learning by doing and fueled by our passion for technology. We value creativity, persistence, and innovation. Integrity and living meaningful lives are the foundations of all our values.
Okay, so as you can see here, there is some typing in the background, but you have to admit it's working pretty well. And this is actually something that we had few dilemmas about this. Basically, if you are trying to implement denoising, I mean, is it really okay? Is it good if you remove every noise in the background? I mean, in that case, we had few solutions like that, but I mean, they are used by our competitors and so on. But in those cases, you just don't have a natural voice. I mean, it just doesn't sound right. I mean, you have a guy which is clapping and so on, but you just couldn't hear anything. So we actually tried to implement something which is not denoising as speech enhancement. We are trying to make the noise much less, but at the same time just to improve voice of our customers. And then maybe...
Denoise.
Yeah, this is the raw audio.
We are the humble engineers led by our philosophy of learning by doing and fueled by our passion for technology. We value creativity, persistence, and innovation, integrity, and living meaningful lives are the foundation of all our values.
And now with denoising.
We are the humble engineers led by our philosophy of learning by doing and fueled by our passion for technology. We value creativity, persistence, and innovation. Integrity and living meaningful lives are the foundations of all our values.
Okay. So now I will try to show you another example, which is actually recorded in our language. But I must say that this neural network was trained on a few languages, German, Japanese, Spanish, English, and so on. But our languages, Bosnian, Serbian, Croatian, and so on, are not in that list. So you will see how it's working on generalization part. So this is also recorded from our platform. Now you will hear a different speaker.
Jedan razgovor sa šumom iz call centra, gdje se čuje i telefon i sve ostalo. I sad trenutno je isključen denoising. Sad evo trenutno sam uključio naš denoising, tako da vidimo kakva je situacija, da li je bolje. Evo opet isključujem denoising.
So
I evo sad opet uključujem denoising. To je što se tiče tog šuma.
Okay. So you can see this solution is definitely not perfect, but it's actually working well, and it just can be used in real world. So basically, that was our first idea, and I think we succeeded in that. At the same time, this denoising part is actually a hot topic in today's world. Because, for example, Google, Teams, and some other large companies actually developed their solution a year ago or something like that. So basically, there are still many improvements in this area. And this is actually pretty interesting because you have different languages. You have different types of noises. Sometimes something is not noise. For example, if you are trying to play a music or something like that, maybe that's not a noise. You are just trying to show a song to someone else. So there are many traps where you can see that your system is not working well, or actually it is working unexpectedly good. And of course, this everything makes it. I mean, we have a great room for improvement in each of those solutions, but we'll see what will happen in next few years. Okay, so thank you. Any questions?
Yeah. Hi, Sead. Thank you for the presentation. Are there any questions? Oh, over there. Okay.
I'm also surprised.
Oh, there is the microphone.
So, does the noise suppression create delays in the sound when talking?
Yeah, but not that much. So as I said, we are taking last 40 milliseconds from the call, which is something you just cannot hear. But we are adding the delay of 20 milliseconds to that. Because of those 40 milliseconds, we are denoising last 20. So we have those 20 milliseconds which are just necessary. And then the whole processing is actually done in less than 10. So basically, our denoising system is making a delay of 30 milliseconds, which is just not something you can hear.
Okay, thank you.
Thank you.
Any additional questions? Somewhere in the audience? No? Oh well.
Okay.
Thank you very much for your presentation. I forgot to get you your certificate, but thank you very much. We really appreciate it, and we thank you for the innovative project that you presented to us.